Did we get this side too?
Sorry.
Yeah.
Wish you wouldn't mind.
Yeah.
I think, turns out the problem, why it was stopping recording is because there wasn't any space left on my phone.
Did it record that other part that we pressed record to?
Yes. It tried to.
Did you make space in your phone?
Sorry?
Did you make, yeah?
Turns out I still had a bunch of the first lectures that I recorded on my phone saved to it. So there was just tons of hours of footage that has already been uploaded to YouTube that didn't need to be on my phone anymore. Alright. My allergies are spiking today, so I'm sorry if I sound sniffly or if I sneeze 8 million times. How you guys feeling today? Okay, so for this class, the test is live. Some people have already taken it. Is anyone in the room one of those people? Okay, 50-50. To those who have yet to take it, do you have any specific questions about new materials or going into the test? Anything you would like answered or you'd like us to talk about? Okay. Please do ask those types of questions at any time. But with the lack of anything specific from you guys, I would like us to start looking at waves, because it's very important. You see and hear everything utilizing waves. Before we do that, I do want to make one brief announcement. There is, at the start of 1500, did you guys take do you recall, I'm fairly certain you all did, do you recall having taken a sort of like intro prognosis test, like 30 minutes, multiple choice Scantron, just to see everyone's entry level point? Does that sound familiar?
I do not. Did
Maybe
you?
a couple months.
I did not remember that.
Well,
We
there's
did
a closing one too. So we do have to do that at least at some point before the semester ends. I don't have it prepped yet. Not everyone's physically here.
It doesn't count.
No, it does not count as a grade. It's purely for departmental statistics to see how we're teaching specific things based on your entry level position and growth. So I'm not entirely sure exactly what day that's going to happen. It may end up needing to be the last day of class that we'll meet, just to make absolutely certain that we get it in, but everyone will be here. We don't have anything else urgently going on except exam studying. But that is on the horizon. That will be something that happens at some point in the next 1, 2, 3, 4, 5, 6 class meetings.
Our last class is on a Tuesday, correct?
Correct.
It's Thursday, there's none.
There's no class Thursday. Exam starts. There's no class Thursday, May 6th. I believe exams start Friday, May 7th.
And when
So,
you
yes.
open yours, do you open it the Friday or?
Pardon. I will open mine on the Friday. And the last similar situation of tests, they'll last through the exam season. You can just pick your best time.
Will we get like more time on the final exam? Or are we still gonna get only 5 hours?
Or like,
I'll probably bump it up to 6, maybe.
Just because the one yesterday took me like almost 3.
it took me almost 4.
But I think that almost because like I think I did it sooner, but like in the first part I ran into the unit error. I realized I was using the wrong hours, I had to rework everything, and then I had to go back and do something.
Oh my god, don't say that. I do not remember saying, oh my god. Okay, it's okay. It's okay.
Just because most time I feel like I don't think they like the ends on the EV guys from taught. It's like that's not regular units.
It's not.
That
But this is why I'm going to
Okay.
be manually grading it.
Right.
Okay, yeah.
the sign is just a way that conveniently puts the answers there in front of me all together at once, and sometimes actually grades them correctly.
Nice.
Only sometimes. Okay, so brief 30-minute max Scantron affair. Nothing to worry about, just something that we have to do. Now, to start with, or to begin.
Wait, had you said that since we would have just learned the wave stuff that's like a majority of our exam, or is that another?
It will not be a majority of the exam.
This would be part.
Yes.
Okay.
The exam will be cumulative of the entire semester. Most of the semester was everything that came first. So this will just be extra things added in, like 45% heat and thermal, 45% electricity, maybe 10% sound concepts, or waves concepts, maybe.
Mhm.
That's probably 10%, probably pretty generous, actually. Okay. I will post these notes. We'll spend enough time on this to make sure that everyone has a good understanding of the material. Do please interrupt me with pressing electricity questions, because right now there's still a test active. Talking about that's the priority. But at least to start this particular topic, so we have some more time for it, waves encompass both sound and light. Optics is the study of light and how it bends. So they are very important to at least two of the major senses that most humans have. Now, the actual definition of a wave it might be a little weirder than someone would first guess. And there's no wrong answer here. Just first thing pops in your head when you hear the word wave, where does your mind go?
Ocean.
Ocean. That's perfectly valid. That's where the word is most commonly used in English vernacular. And an ocean wave is a good example of a wave. This is just like a series of waves, one after the other, a series of the surface of the water being blown and moved by the wind. But by the definition of a wave, the water itself is not actually the wave. A wave is traveling energy. When you see ocean waves, you are seeing waves travel, but the water moving isn't the wave itself. The wave is the energy traveling through that water. All waves, regardless of type, regardless of how they were made or how they travel, are traveling energy. The wave itself is energy moving from point A to point B. The water, in the case of ocean waves, is simply the medium through which the wave travels. When waves pass through something, typically speaking, the medium. So, where is that for somewhere? Yes, a ripple traveling through a mechanical medium. This is medium in terms of like the substance being utilized in this situation. So, ocean waves, like the wave is the energy, but the medium the wave is traveling through is the water of the ocean. Another very good example of waves with medium is sound. As I'm speaking, I am making the air vibrate. Sound waves are just air vibrations, like ocean waves are ocean vibrations. But even though I'm making the air move, notice that the air doesn't actually travel with the sound. The energy is what travels. In the case of my voice, in the case of the ocean, the energy is what is going from point A to point B, not the medium. In the case of ocean waves, every single wave that comes in all of the water wrapped up in a single wave does not travel with the wave all the way onto shore. Because then the next wave would just bring in more water, the next wave would bring in more water, and Earth would have no surface. It's a little more obvious with sound waves, though. As I speak, I am putting energy into the air, and that energy travels using the air as a medium from my throat to your ear. The energy is the only thing actually going from my throat to your ear. The air itself, it does vibrate in place, but the air does not move towards you. If it did, every sound would come with a bluster of wind. Which can happen, but thankfully for my career, I do not create typhoons with my voice. So the medium does not travel. The actual wave itself is simply the traveling energy that occasionally will go through another object and use it as a physical medium. So, main takeaway. The first sentence right up here, big thing to remember, wave is just traveling energy. That is the wave itself. I'm going to skip around a little bit here. Well, that's frustrating. This slideshow is only about light. Where are my sound notes? Pardon me, everyone. Minor technical difficulties. Optics. Oh. If I had sound waves, they appear to have been eaten by the internet. Sorry if I said if I had sound notes. That is unfortunate and rather bizarre. Okay. Well, I'll leave this on screen for a second, because I'd like to talk about the things that all waves share before talking about specific kinds of waves. All waves are traveling energy. And really that's the only thing traveling. The water of the ocean and the air do move somewhat, they do vibrate, but they don't travel. Say for example with that ocean wave, the wave is what will travel along the ocean, and as the wave reaches a certain part of the ocean, specific water molecules will move up and down as the wave passes through. Might even rock back and forth a little bit, but it doesn't all keep traveling in the same direction as the wave.
What kind of energy travels through the wave?
That depends on the type of wave that it is.
Well, like the ocean wave.
That would be mechanical energy.
From
the wind, the spin of the earth.
Oh, okay.
The ocean waves are created by a lot of different things. I think wind is the main propagating factor.
Wait, what about kinetic?
Sorry?
What about like kinetic?
Kinetic energy is a type of mechanical.
Because it's like also potential, right? Yeah.
Yes, mechanical can also include physical potential energy. So yes, an ocean wave is basically traveling kinetic energy.
Mm-hmm.
You can think it's kind of like a series. In the case of an ocean wave, it's like a series of collisions. One particle will have energy and bump into the next one, and the energy just keeps transferring all the way down. So for an ocean wave, it's kinetic energy. And same. Yeah, let's go ahead and make this distinction now. There's lots of different types of waves. Most waves have, like, for each category, there's usually a sort of a binary split between how a specific type of wave functions. This particular set of categories is, the dichotomy here is the wave a physical wave made of kinetic energy traveling through physical objects, or is it not that? So this is the starting of the classification of different types of waves. Mechanical waves are the type that we've already talked about. Energy traveling through physical objects. And let's call that physical medium. This includes ocean waves and sound waves. And a mechanical wave is always made up of mechanical energy, which is pretty much always going to mean kinetic, because if you're making physical matter move, there's kinetic energy involved. And this category contains most of the types of waves that you have seen and visualized and would regularly recognize as a wave. Ocean waves require the physical medium of the ocean. Sound waves require the physical medium of air. Earthquakes require the physical medium of the ground. Earthquakes are as a result of seismic waves. In the case of an earthquake, say the quake itself happens because two of Earth's plates jam up against each other in an unfortunate way. That releases a bunch of kinetic energy into the ground. The energy is the only thing that travels from the San Andreas Fault to Sacramento. The ground itself does not all travel that entire distance. Like the rocks from the fault line do not make their way to Sacramento, but the energy does, and that's the problem. So, mechanical, physical waves, all the types that you tend to think of. There is another type, which we'll probably spend most of our time talking about, because it's the type that's hardest to describe and visualize, and that's electromagnetic waves. This encompasses light and all other types of electromagnetic radiation specifically. I've been reminded recently that chemists refer to some particles as radiation. The alpha particle and the beta particle, certain nuclei being ejected from a particle are counted as radiation in chemical circles. They're less considered to be traditional radiation in terms of physics academia. When I say the word radiation here, I'm mostly referring to electromagnetic radiation, which is gamma rays, X-rays, things of that description. Technically, an ejected alpha particle is not a wave. But gamma, micro, radio, etc. all are types of waves. These types all are just a family of the same thing but different flavors. And these, instead of being made up of kinetic energy traveling from one point to another, these are made, and this is the tricky part. I think I should have a slide for this. Yes, it's sound waves that aren't in this show slide set or something. There we go. If you could somehow grab a beam of light and study it, it would be something similar to what's on screen now. Light is an electromagnetic wave. That means it's not actually a physical thing. It's functionally just traveling energy that was shot in the form of a laser. And that energy is traveling in the shape of one oscillating magnetic field and one oscillating electric field, both perpendicular to each other, but traveling to the same direction. Traveling in the same direction. The last chapter we talked about how magnetism is weird and how it has a weird perpendicular interplay with electricity. This is the next step of that. The E field and the B field oscillate perpendicularly to one another. In this particular drawing, the B field is oscillating in the Z plane and the E field is oscillating in the Y plane, but the wave itself, both fields are traveling forward in the x-axis. And they have to be traveling together to actually form the wave. This is what the actual individual light photon is made of. And because this is even purer, raw traveling energy, because it is in the form of the E field and the B field, and those can exist on their own, these waves don't require a medium to need to travel. If I was in space, I could scream all I want. There's no air for the sound to propagate through. But light can travel through the vacuum from the sun to Earth unimpeded, because this type of radiation, these types of waves don't require a physical medium. They can travel through one. You're seeing everything you've ever seen has been light through air or maybe through water. So they can travel through a medium, they just don't have to. And these are the broadest categorizations for most types of waves. If you've actually seen the wave happening, it's probably been a physical wave. Ironically, even though we see using light and electromagnetic waves, you probably haven't seen an individual photon. I haven't, at least. So, despite the two very different natures of waves, there are some things that all waves do still have in common. The energy travels from point A to point B. Light is energy traveling from the sun to the earth. Sound is energy traveling from my throat to your ears. It's still energy going from point A to point B. If there's a medium involved, the medium itself is not traveling. And there's some sort of oscillation involved. Is that term unfamiliar to anybody? You know what, I should define it anyway. Oscillation, repeated motion, forwards and backwards. So what you're seeing on screen, the movement of the E field and B field waves, is an oscillation. At any given part of the wave, the E field oscillates up and then down and then up and then down, and same for the B field, back and forth, back and forth, back and forth. Any repeated motion that is continually going back where it came from is a type of oscillation. And it can be physical oscillation or it can be field oscillation. There still has to be something shaking. Other forms of oscillation include jump rope and I don't know what the technical term is, the part that hangs down from a grandfather or a cuckoo clock. As that's going back and forth with a continued motion over time, that's technically an oscillation. So waves, traveling energy, there's some form of oscillation involved, and there's some commonalities about how we measure all of these types of waves. all waves have something called an amplitude. This is its literal physical size. Say an ocean wave passes you that is 1 foot tall. That would be its amplitude. If you were able to measure from the water surface up to the peak of the wave, that would be its amplitude. And a 1 foot tall wave does not have as much of an amplitude or is as scary as a wave with an amplitude of 1 meter. The physically larger a wave is, the bigger its amplitude, and that's a measurement of how much energy the wave is carrying. The more energy involved, the more particles it's able to move in any given moment. The bigger the tidal wave, the more energy it adds. And amplitude is a physical measurement, which means we can measure it in meters. In the case of a sound wave, amplitude would be a measure of its volume. The louder I yell, the more energy I'm putting into the air, the bigger the wave.
What? Like a circle? Wait, no. Volume.
Sorry, like sound volume.
Oh, okay.
Not capital V, three-dimensional space volume, audio level, crank it up louder volume. All waves also have a physical wavelength. And that's literally the physical length of the wave. What I've written here is wavelength. The variable for wavelength is lowercase gamma, which appears to be a weird Photoshop letter Y. Because it's a physical length, we measure it in meters like we do with amplitude. So if you're watching ocean waves, you can physically take a tape measure and just measure how long it is. That's its wavelength. I'm not trying to trick you with that one. It is worth noting though, one full wavelength, like one whole wave, is defined as from one point to the next point in of that type in the wave. So if you were measuring wavelength, it has to go from the start of the wave through a whole oscillation and then back to that same part of the cycle. You could measure wavelength from rising edge to rising edge. You could measure, if you wanted to, from peak to peak or from trough to trough. As long as you start in one spot and measure to the next iteration of that spot. It has to go through the full cycle to be considered one full wave. So, all waves have these two things, and there's one more thing that all waves have, and that is a frequency. I would assume, based on what I've heard in common American English, that you've heard of the unit of hertz before. Maybe not within precise physics context, but at least heard the word used as a unit, or at least heard the word.
Isn't it like 1/s?
It is 1 over time, yes. Yes, actually, 1 hertz is equal to 1 over 1 second. It is an inverse second. So I'll write it down. 1 hertz is equal to 1 inverted second. I'm going to call that s to the -1. So hertz is an inverse of seconds. And the reason for that is the frequency of a wave tells you how frequently that wave passes you. You could watch the ocean and with a stopwatch measure the time it takes for one full wave to pass you. So you start the stopwatch when the wave is rising, you let it run until the wave is rising again, and you stop the stopwatch. You measure like 5 seconds. That would be the time for one wave to travel in normal seconds.
The period.
The period, very good. Period of oscillation. Frequency is just the inverse of that. You take that 5, you invert it, the frequency would be 1/5. Because whereas period of oscillation is seconds per event, frequency is events per second. So a wave with a frequency of 1/5 hertz means that one event happens every 5 seconds, or 1/5 of an event happens every second. It's a measure of how frequently something happens. And frequency ends up being important because it tends to be, for most waves, the main thing we measure to identify like the specific wave it is within its family. For sound waves, frequency determines exactly what pitch you're hearing. For light, frequency determines what color you're seeing. So different waves of the same type can have different frequencies, and that does affect your perception of them.
Wait, so for like ocean, is that like how fast the waves are coming? Like they must be going like.
It's a way of determining wave speed. Waves do still have a normal speed. There's a formula for it. There is a normal formula for wave speed, which is separate from, okay. This is the formula for wave speed. Waves do have a velocity. The energy is traveling. You can measure how fast it moves in general. You can clock it. And you can do that by simply dividing meters per second like you normally would, distance per time. But this formula here accomplishes the same thing, but in terms of describing the type of wave you're looking at. Because frequency times wavelength is hertz times meters. 1 hertz is 1/seconds. So it's the same velocity formula as before, just using the wave's innate properties.
So like you increase the frequency, you increase the speed.
If the wavelength doesn't change.
Yeah.
If you keep wavelength constant and increase frequency, yes, the speed will increase.
Can you even keep one constant? Not really, right?
Within sound and light, no. Sound and light, again, the two main things most people perceive as waves as humans on Earth, most commonly. Sound, both sound and light have a cap speed on planet Earth. Sound's velocity is, and this one has caveats, in room temperature, standard surface level atmosphere air, the speed of sound is 343 meters per second. And as long as your pressure stays the same, you're still on Earth's surface, and the temperature stays the same, that number is constant for sound waves. On the other hand, the speed of light is constant no matter where you are.
But why? Because, like, what if you... Doesn't it seem like the speed of light should be faster in space than here because it has a medium here?
In a manner of speaking, okay. You're not wrong. I want to preface this statement with, I want to preface everything I'm about to say with, you are not incorrect. We consider the speed of light to be constant throughout the entire universe. Largely because it makes all of our calculations a little more convenient. Different parts of the universe might seem like light is traveling differently because 1 second or 1 meter might be different in a different part of the universe due to the way space-time might bend or not bend if you're in the empty void. Alternatively, light should theoretically travel at its fastest through the void of space, where there's nothing to hit, nothing to slow it down or bend space-time around it. When light enters Earth's atmosphere, on some level, it simultaneously remains at the same speed and slows down.
Maybe not as much then, right?
It's still, like, we still clock it at the same speed, but when it enters the air of the atmosphere, its frequency shifts.
Like lower?
I think so, yes. So in a manner of speaking, there's fewer waves per second, so it did slow down, kind of, but with its new wavelength factored in, the actual velocity of the energy remains the same. It's weird. And since this is technically a magnetic phenomena, that's probably why it's weird. Magnets. So, within certain boundaries, these speeds are capped. This speed pretty much always capped. We consider this to be a constant no matter where you are. The speed of sound will fluctuate because sound requires the physical medium of the air, so interfering with the way the air behaves will affect the speed of sound. Typically speaking, the higher up you go in Earth's atmosphere, the slower sound gets because the air density is lower, there's fewer particles to vibrate.
Slower?
Yes, speed of sound gets lower the higher up you go. I think additionally, the temperature has an effect on it as well. I just don't remember if hot or cold specifically makes it faster or slower. I don't remember which direction.
I feel like it's hot.
I always remember it not being what I expected to be.
So then maybe it's cold.
My initial thought would be making it colder would make it go faster because the particles would be bunched closer together. But because I remember it being opposite what I expected, it must then mean it's faster in hot air. I will check that. Yes, colder air makes sound travel slower. You can only assume hotter air is more energized and is more primed into a state to naturally ping off of each other and keep moving. That's my best guess.
Well, hotter air has more energy and more movement, so easier for the sound to go through the movement.
That would be my best thought, yes. Hotter air is already moving, and so is already moving faster, so it might be easier to facilitate the continued movement of the energy. Speed of sound will also change depending on what the sound is traveling through. This is specifically room temperature air. It's about 5 times faster in water and even faster through solids.
Wait, it's faster in water?
It is. If the medium is more dense, that makes it easier for the sound to travel. Ironically, light works in the inverse. Light doesn't travel through solid objects. Most solid objects, if they're opaque. This isn't a trick that comes up commonly in modern media, but on the off chance you have seen it, have you seen in, say, a show or a movie, or maybe even heard about a trick where someone might put their ear to the ground or onto a railroad track to try to hear if there's a train coming, or hear if there's a stampede, or maybe to hear if there's a car coming up on the highway?
I've never seen that.
Okay, that's fair. It's a trope that has become less common in media these days. But
Does that work?
it does work.
Because it's more dense?
Yes, if, say, you come up to a railroad track, all over the place in
This
Clinton.
is dangerous.
It is dangerous, but if you need to know if there's a train coming, first, hear normally, do you hear train? Then, put your ear to the rail, and because sound travels faster through solids than through gas, the vibrations that the train puts into the tracks will travel faster through the tracks than through the air. And even though we don't really hear through solid objects, you can still tell that there's vibrations, because this is the part of your body most sensitive to vibrations.
Wait, what do you mean we don't hear through solid objects?
Well, your ear was designed to work in air.
Well, like, but like, if I'm in a room and then someone else is in another room, like, I can hear through there.
Oh, what I mean is you cannot put your ear inside of the steel and expect your ear to function correctly.
Okay.
You can't put your ear into the solid. Ears are designed for the sound to travel through air,
Okay.
which is why I think sound weird underwater. But because this part of your head is still very sensitive to physical vibrations, you can put that onto the rail, and the vibrations from the rail will transfer into your head, and you will hear them. And if there's vibrations you sense that way, you know that there is a train nearby.
Wait, you feel or you hear?
At that point, it's closer to feeling it than it is to hearing it. Because, again, we only really hear through air. The eardrum in our ear is designed to accept air vibrations.
So if we hear in water, it's because there's air, or is it because we're not?
It's either the vibrations in the water are hitting the air that's still in your ear, and then the energy travels through the air to your eardrum, or it's that your ear has completely filled with water, and now the water is what's hitting your eardrum. I'm not sure, honestly, the mechanics of whether or not your ears completely fill up. I'd rather they didn't, because I got a nasty ear infection from a lake once. I don't want to repeat that. Okay. I've been hand waving and giving you a lot of just details, not a whole lot of numbers or things, but I think this is a good foundation to continue talking about waves. That said, if you haven't taken the test yet, do prioritize studying that, and if you have questions, email me or bring them next time. I would much rather review that if you have the questions than force new information down your brain while you still have questions. So do keep studying, do let me know, and send me questions as you're taking the test too, because I'm basing this on the fact that if we were taking it together in person, you'd be able to ask your questions. So send the questions, I will answer them. I'm rambling at this point. You guys can go on. I do hope you have a wonderful day. Do also remember, I will see you tomorrow, but I'm still saying it in all my lectures today. There is lab next week. We're building motors, should be fun.
Is that the last one?